In this lecture, we're going to look at the problem we first saw at the end of last lecture, which is overfitting. When our model is being trained and the parameters we're finding make it fit too much to the training data and then lose the ability to generalize outside the training data. So we're going to first look at how to estimate this true error. That is the error our hypothesis after training the model will have when on average applying to any new example. And then we're going to see how to prevent overfitting. And basically there are two approaches here. One is selecting the most adequate model for the data that we have. So one that can fit the data but still not lose the ability to generalize outside the training data. And the other is regularization. Basically, we are going to change the way we are training the model in order to try to minimize this overfitting, to try to prevent it from fitting too much to the training data. So in the last lecture, to recap, we saw this idea that we are fitting a model to the data. The model gives us a way with using parameters to cover a hypothesis class. And when we fit the model, we are selecting one hypothesis, and we do that by optimizing some function of the training data. For example, minimizing the quadratic error when we are doing regression. If we use more powerful models, then we can adjust better to the data, and we can find hypotheses that come very close or much closer to the training data that we have. We can do this, increase the power of linear models by using nonlinear transformations of our data into higher dimensions, and this allows us to approximate more and to do things that would be the equivalent of creating curves on the original space of our data. And we can do this without limit. We can just increase the power of our models in this way with no limitations other than any computational limitations in practice. But the problem of this is that once the model becomes too powerful for the training data we have, we start having overfitting. The model is sacrificing performance outside the training data because it's fitting too much to the data we're using to train it. So, for example, if we try to fit this set of points, these red points here, with a straight line, we can find the best hypothesis on the hypothesis class of all the straight lines, but it's still not a very good fit because this is a straight line and our data has this curved shape. If we do this manipulation first of projecting our data with a nonlinear transformation, in this case a polynomial transformation, into higher dimensions, then in fact we end up fitting a polynomial curve in the original space, even though it's still a linear model in this higher dimension. And this can improve the fit. So in this case, we have a curve that fits much more closely to the training data that we're using. The problem is, if we go too far, we start having overfitting. So we start having a hypothesis. The hypothesis that we find is very close to the training data, but starts making predictions that are very suspicious outside the training data. So the first thing that we need is to measure these different types of errors. Our goal in the case of regression is to find this approximate function that maps between the features and the target value that we want to predict, based on a set of data for which we have both the features and the target value for each example. So this allows us to do supervised learning because we can always compare the target value that we have for a particular example with the output that our function is giving us as we change the parameters. So we're going to fine-tune the parameters to minimize the error between the prediction and the target value. So the training error will be this error that we can measure on the training set. The problem with this is that the training error is not a good indicator of how well our hypothesis will perform in new examples, because we are specifically adjusting the parameters of our model to minimize this error. We're going to find the hypothesis that minimizes the training error, but it may be overfitting and make the error outside the training set much higher. So this training error is a biased estimate of the actual error that our model will commit, because we are on purpose adjusting these parameters to minimize the training error. So we are making it so that for this particular data that we are using in training, the error is as low as possible. Now, the problem is, how can we estimate the performance of our hypothesis on the whole universe of data when we only have a sample of the points from there? If we use these points for training, then our estimate of the error, which would be the training error, will be completely biased and not give us a realistic estimate of the error for the whole universe. So the solution is to measure the error outside the training error. The training set, because the training error measured in the training set is very biased. But if we measure the error on some points that we are not using for training, then we have a good estimate of the true error. We are estimating how the hypothesis will perform outside the training set. Okay, so let's split the data. Let's say we use some points here in blue for training, and we leave out some points for testing at the end. And this test now gives us an estimate of the true error. Note that this is not the true error. The true error is the average error over all the universe of points, and we cannot measure that because we don't have the whole universe. This is an estimate because we take a sample of points that we are not using for anything, and then we use that sample to measure the error, and this gives us an estimate of how well this curve will perform outside the training set. So doing this is called the test set. We have an estimate of the true error for our hypothesis. But note that this estimate depends on the sample. So it depends on the points that we have here, and it depends on the split we did between the training and the test set. So if we redo the split at random, we get different points on the training set and different points on the test set. We get slightly different curves for each sample, and we get slightly different values of error on the test set. So even though the true error of the hypothesis could be the same, or the true error of our model, if we could train it on the whole universe of data, we have this problem that with differences in the training set, we get different hypotheses, and then with differences in the test set, we get different estimates of the error. So this estimate of the true error is stochastic, and it's just one sample out of many possibilities that we could have obtained. However, the test error is unbiased. It can be higher than the true error, it can be lower than the true error, but the probabilities of being higher or lower are the same. And so basically we can say that if the true error is somewhere around here, each time we create a split in our data and train with one part of the data and then evaluate the test error with the other, we get a sample from this curve. Most likely we are close to the true error. Sometimes we are below the true error, sometimes we are above the true error, but on average it will converge to the true error. So it's an unbiased estimate. So basically these are the errors that we are measuring here. The training error is the error measured on the data used for training our model and obtaining the best hypothesis. And the test error is the error measured on a set of points that is not used for anything except to estimate the true error. But the test error is just an estimate of the true error. The true error is not measurable. This is the average error over all the universe of points, but we don't have the universe, so we cannot measure the true error. We can only estimate it using the test error. The generalization error would be the difference between the true error and the training error. So basically this is the error we get by going from the training set to any other point outside the training set. And this is also something that we can estimate if we compare the training error with the test error, but we cannot measure directly because we don't know the true error, we cannot measure it. So let's look at overfitting from this perspective, using the training error and the test error. Suppose that we are fitting our data, so this set of points, and we are increasing the power of our model by increasing those transformations, or if you want, by increasing the degree of the polynomial. So this would be a straight line, degree 1, this would be a quadratic curve, degree 2, 3, 4, and so on. As you can see, when the error measured on the training set tends to go down as we increase the power of our model, because we increase the ability to fit closer and closer to the points in the training set. When we look at the test error, here at the beginning, we also have a high test error. So both training and test errors are high. This is called underfitting because the model cannot properly fit the data. So we are making errors both on the training set and on the test set. This would be an example of underfitting. We try to fit this curved shape distribution of points with a straight line, and we have a high error both on the training set and the test set. Note that the test error can be below the training error or above, but these are all estimates. So there is quite a significant stochastic variation here, and it all depends on where the points fall, if they fall on the training set or on the test set. So don't read too much into these slight differences. It's the overall pattern that is important here. If we increase too much the power of our model, we start having a very large test error, even though the training error is small. So we have a very large difference between the two. This would be an estimate of the generalization error. And we clearly have the model adapting too much to the training data, to the detriment of the ability to make good predictions outside the training set. So this would be an example. We have the curve shooting up here, so having a very large error on that point. It goes down here, probably outside where it should be, and so on. So we have a very large error here on the test set, even though the curve falls very closely to the training set. So this is an example of overfitting. We are adjusting too much to the training set and losing accuracy outside the training set. And if we estimate the generalization error by looking at the difference between the training error and the test error, we can see that overfitting leads to an increase in the generalization error. Okay, so what can we do to select the best model? We clearly see that models perform differently. If we use a very simple model, we have a very high error both on training and testing. If we use a very powerful model, then we can adjust very well to the training data, but we have a huge error outside the training data on the test error. So we could look at the point where we have the lowest error outside the training set. This training error is not very informative for deciding which would be the best model, because as we increase the power of the model, it simply goes down, the training error. But the test error gives us an idea that some models are better than others. So we could use the test error and choose, for example, a polynomial of degree 5 here, because it's the one with the lowest test error. Now, the problem of doing this is that, remember, the test error is an unbiased estimate of the true error. So for each of these points, if we take one measure of the error here, the test error, and we take another here and another here and so on, each of them individually come from this distribution that is unbiased. Its average is around the true error. So some of them may be a bit high, some of them may be a bit low. There is some variation here, but they are unbiased. The odds of getting a test error that is larger than the true error are the same as for getting a test error that is smaller than the true error. However, if we do this several times and then pick the best one, what we are doing is actually sampling from some distribution and then picking the smallest of that sample. And this is what I represented here with the red curve. This is what happens if we take a sample of 10 values at random from this blue distribution and then pick the smallest one. And then take another sample of 10 and pick the smallest value, and so on. If we do that repeatedly, we get this distribution here. And note that the peak of this distribution is well below the peak of the blue one. So this means that when we do this kind of thing, we take several samples of the test error, we estimate the test error on different points here, and then we choose the best one. Odds are that this test error that we got here is not around the true error, but it's below the true error. Because since we are choosing the smallest one on purpose, we are increasing the probability of choosing one that happened to fall below the true error. So this makes the error estimate biased, and it's actually no longer really a test error, because the test error should be an unbiased estimate of the true error. Okay, so we see that we now have an additional problem when we are selecting different models, because the very choice of picking the one with the smallest error will bias the error estimate that we have there. So we cannot use the test error to choose the best model, because if we do that, it's no longer a test error. It becomes biased because of our choice. So we're going to need 3 data sets. We use the training set to fit the parameters of our model and choose the best hypothesis in the hypothesis class according to the training data. And this would be our hypothesis. Now, if we want to select different models, between different models, we can do this for each model, and we use a data set outside the training set to choose the best hypothesis class or the best model. And this will be the validation set. This is not the test set because we are using it to choose the best one. And when we choose, we make the estimate biased. So the validation set will also be biased because of our choice of picking the smallest one here. So if this was the validation error, by picking the smallest one here, we would bias the estimate of the validation error. So the validation error as an estimate of the true error. So then we leave out some points for the test set that we do not use for any decision, and we only use for estimating the true error of the final hypothesis. After we do everything, select the best model, train it, and so on, we use the test error to have an unbiased estimate of the true error. We're going to see better ways of doing this, a bit more complicated, but this is the general idea. Every time that we are making decisions in order to minimize the error, whether to fit the parameters by minimizing the error, which we do on the training set, or to choose between different hypothesis class or other parameters, which we do on the validation set, our choice biases these estimates, and they'll tend to underestimate the actual error of our hypothesis. For that reason, we need the test set to have an unbiased estimate of the true error at the end. Another approach, aside from selecting the best model, would be to use regularization. So basically, with model selection, the example we saw here, we try different hypothesis classes, different models, and we pick the one with the lowest validation error. So this would be in order to minimize the problem of overfitting and to get the best generalization out of our final hypothesis. But a different approach is to change the learning algorithm in order to prevent it from fitting too much to the data. We can have an intuitive idea of this when we look at overfitting examples. For example, here is that the problem may be because the curve can be too flexible, and then it starts shooting off into different directions and does strange things. If we could make the curve a bit tighter, a bit more resistant to curving so much, then we could minimize this problem here. And that is the idea of regularization in general, is to change the learning algorithm to make it a bit stiffer, to make it a bit more resistant to adjusting too much to the data. One example in regression is to add some penalty as a function of the parameters. For example, in ridge regression, we use this quadratic penalty on the parameters. We have here the quadratic error that we're trying to minimize. So we're trying to make the predictions of our hypothesis as we change the parameters as close as possible to the actual target values for all the examples. So this is minimizing the quadratic error that we saw last week. But we also add this regularization term, which is the sum of the squares of all the parameters. So if the parameters are, for example, the coefficients for the different terms of the polynomial, this is the sum of the squares of all those coefficients multiplied by a scaling factor that we can adjust. So this allows us to give more or less weight to this term here. And what this does is to penalize having parameters that are too large. So this makes the curve a bit stiffer by trying to shrink the size of the parameters and find a balance between the error to the training data and the flexibility of the curve here. So this would be one way of solving the problem. Let's suppose we have this data set here. We have here a training set in blue. We have a validation set here in red, and we can use this to choose the best regularization term for ridge regression. So this value here, this lambda, is what we are trying to optimize here. If we have a lambda of 0, that is, we have no regularization, we have this blue curve here. It goes down and up and down and up and so on, and it passes through all the blue points very well. So it has a very low training error, but then it has a huge validation error because it makes these strange curves all over the place. If we add a bit of regularization, we can reduce the validation error quite a bit. So it goes from millions to 0.2. We increase the training error a bit because now the curve is a bit stiffer, and it's this one here, this cyan curve here. Sorry, the green curve here. So it's a bit stiffer, but it still can follow more or less the points. If we increase the lambda too much, then we start giving too much weight to this term, and it starts reducing the ability to fit to the data. So at some point, using too much regularization starts to actually increase the validation error too, because the curve starts to become too stiff. So basically, with regularization, we are not changing the model. We are always using a polynomial of degree 15 here, but we are adjusting the way the model is trained, how it fits the data. And by changing the weight of this regularization term, we can make the curve more or less stiff, and so try to optimize in order to keep the ability to follow the data, but not go too wildly on the predictions, and so minimize the validation error. And in this case, a 0.1 value of lambda would be the best of these values that we tried. Okay, so let's see a more real-life example with messier data. This is a table we can get from Index Mundi, this site, which has life expectancy and GDP per capita for different countries for 2003. So this is how the data looks like. If we plot the data, we have life expectancy here in years and per capita GDP in dollars here below. And now we want to try to fit some curve here to try to find a relation between GDP and life expectancy. Now, one problem that you sometimes have in real data is an issue with numerical stability. So if you have things like one scale is varying from 20 to 90 and the other goes up to 50,000 or more, and if you have very large values and you do things like a polynomial regression where you are putting this to the cube and to the fourth power and to the fifth power and so on, you can have problems with numerical precision, because if you try to add very large numbers and very small numbers, the small numbers will be outside the precision of the floating point representation, or you can even have floating point overflows or things like that if you have very, very large numbers. So we need to be careful when we have a large range of values, and it's always a good idea to rescale things. We need to know how we rescale, because then we need to rescale back if we want to do predictions or something like that. And we're going to see several ways of doing this rescaling. But in this case, I'm going to simply rescale all these values to a range between 0 and 1. So basically, I take the maximum life expectancy and divide all life expectancies by that. And I take the maximum of the GDP and divide all the GDP values by that. So everything becomes in a scale between 0 and 1. And we're going to split these 180 countries. We're going to use 90 for training, 45 for validation, so that we can select the best model or the regularization parameters. And then we're going to leave out 45 for testing, so that we have an unbiased estimate at the end of how well the hypothesis that we chose is performing. So this is just an example. I'm going to start in these first examples by showing all the steps of how I'm doing things. But then as we go along the course, we're going to start using code from the libraries, from scikit-learn and so on, to simplify the code. But from the beginning, it's best for you to see everything step by step. So let's write here an auxiliary function just to split the data at random. Our data will be a matrix which has each example in a row, and we specify how many points we are going to leave on the test set. So basically, using this NumPy library, it makes it easier to manipulate these data structures. We're going to get a NumPy array with a range of values from 0 to the number of points that we have on our data. So actually, if we have 100 points, this will be 0 to 99, but it gives us 100 indexes, and it fits the indexing of Python, because Python starts all indexes at 0. And now we're going to shuffle this. If you use the shuffle function from NumPy random, it shuffles in place. So it actually changes the order of the values on this array. So here we have a set of indexes that are randomized. They go from 0 to the number of points that we have, and they are in a random order. And now we can select for the training set all the points, all the rows in our data for which the rank is equal or larger to this value for the test point, and for the test set, all those that are below. So if we want 50 test points, then those that have ranks from 0 to 49 will fall on the test, and those that have above that will fall on the training set. And since this ranks array is randomly sorted, we do this at random. So we are picking a random set for training and for testing. And now we return these two. So this is the notation for indexing two-dimensional arrays in NumPy. This tells us which rows we want. It's just a vector of true and false when comparing all these values to the number of points we want. And this indicates with the true flag which rows we want here. And this just tells it we want all the columns for each row. So we are basically splitting the matrix of data points into two submatrices by selecting rows at random. Okay, so using load.txt, we can load a file like this into a NumPy matrix, and then we scale everything. So if you do this, get the maximum for our matrix on the axis 0. The axis 0 is the rows axis, so it will compute the maximum of the first column and the maximum of the second column and give a vector with the two maximum values. And then we can rescale by dividing all the rows on data by the scale. NumPy allows us to do this broadcasting and do this operation in one go. If you're not familiar with NumPy, this is not a problem. You don't need to understand everything now, because we're going to do this on the tutorials and you're going to experiment a bit with this data manipulation. So after a few tries, you're going to use this a lot more easily. Don't worry too much about trying to memorize all the details now. This is something to be learned by practicing. But for this particular case, what we're doing is rescaling everything between 0 and 1, then splitting our data into two sets, one for training and another for splitting into validation and test. And this way we get 90 points for training, 90 points for this temporary array, because we have 180 countries in the beginning. And then we split these 90 points into validation and test. So this is what gives us 90 for training, 45 for validation, 45 for testing. Okay, so now let's try to find the best model when fitting a polynomial of different range, different degrees. Let's start, for example, with degree 1, which is a straight line, then degree 2, and so on, and we'll go all the way to degree 8. So this is what I'm doing in this loop, with degree going from 1 to 8. The range constructor here in Python gives us an iterator that goes up to the highest value we give here, the second argument, but does not reach it. This is useful for things like iterating through the elements of an array by giving the length of the array, because Python uses zero-based indexing, so the index of the last element is the length of the array minus 1. But this is, again, another thing that you can better learn with practice. So basically, we are looping through different degrees of the polynomial. We are going to fit the polynomial using our training data. So this is the x, the first column, and the y is the second column. And we are going to fit the polynomial with the degree specified. And then we're going to compute the error on the validation set. And to compute the error, we simply compute the predictions of our polynomial for the x values in the validation set, and then compute the mean of the quadratic differences, of the square of the differences between the prediction and the data. So this is the mean quadratic error between the predictions of our hypothesis with those coefficients and the validation set. So this means that for each degree, we can train the model, obtain a specific hypothesis, a specific set of coefficients, and measure the prediction error of that hypothesis on the validation set. Now we just check if this is best than the best error so far. We start with a very large number and we store the degree there. So at the end, you can just say what is the best degree that you find, and you can use the same function here to measure the error on the test set. So in this case, the best hypothesis that we found so far, we're going to check the error on the test set. Note here this difference. The validation error is being used to select the best model, or more specifically, the best hypothesis in this case. But then the test error is only used at the end to get an unbiased estimate of the true error of that hypothesis. We cannot use the same set we are using to select hypotheses to then estimate the true error, because the process of selection, of checking if it's better than the other one and changing if it is, this makes the estimate biased. Okay, so this is the set of polynomials that we tried here. We have all the different curves in this case. The training set is in blue, the validation set is in green, and the test set is in red. So here somewhere we can find the best hypothesis is this degree 3, this red line here. And so that was the best one we found using the validation set for choosing the polynomial. And then we measured the error on the test set to get an unbiased estimate. Note, however, that the error estimates will depend on this random split between training, validation, and so on. So especially when we are choosing the best one, we have this set of points for training in blue and the green points for validation. But if they were different points, we would probably end up selecting a different model. So this is very much dependent on this random split in the data. We're going to see later on how we can improve this a bit by averaging over different training and validation sets. But for now, I'll just leave this idea that doing this just once is a bit risky because of all the stochastic noise that we have in these random splits. Another approach we can use is, instead of trying to find just the best model, we can use a high degree polynomial, one that we know that is overfitting. So it can adjust very well to the data if we only consider the quadratic error. But we add this regularization term. For example, with ridge regression, we have this quadratic term for regularization. And this way, we make the model a bit stiffer, or the model is the same, but the way we are searching for the best hypothesis will favor hypotheses with lower parameters, with smaller parameters, and so the curve will be as if it was a bit stiffer, and so we don't have as much overfitting. We can do this using the ridge class in scikit-learn. We are not going to implement this ourselves. The thing is that ridge is a linear regression. So it's a linear model. We input the data and it just does a linear regression with regularization. However, note that we don't have a problem with that. In this case, we use the polynomial fit because NumPy gives us a polynomial fit. But if we need to use a linear model, we can do the polynomial expansion of the data ourselves and then just feed it into the linear model. As we saw last week, these are the same things. So we can solve this problem easily just by creating this auxiliary function that expands the data. So if we have a data set here which has the x value on the first column and the target value on the second column, we create a new matrix that has as many columns as the degree that we want to expand to, plus 1 for the target value. And we're going to use this number of columns for the x, for the input, and the last column for the target value. And for the x values, we're going to do this polynomial expansion like we did last week. So the first column will be the original x, then the second column will have x squared, the third column x cubed, and so on, all up to the degree that we want. So this would be the expansion of our data. If we want to expand to, say, a third degree polynomial model, we would use x squared, and x cubed for the input into this linear model that we're going to use, and keep the target y value there. So let's do the expansion to x raised to the 10 power using a degree of 10 here. This will give us now for our data, for the x, all the values x raised to the power of 1, x raised to the power of 2, and so on, all the way to x raised to the power of 10. And we'll use those 10 values to predict the target value y on the ridge regression. So all of this is the same thing as before. We're going to split the data, and then we're going to use the ridge regression, which is a linear model, but we're going to use it on the expanded data. So this does not take just one value of x, it takes in 10 values of x, which are these polynomial expansions that we created here. So now we're going to change the lambda value. So what we're going to do here is trying to fit what is the best value for this hyperparameter here. So what would be the best balance between minimizing the quadratic error and penalizing for having very large coefficients and curves that are curving too much? To do that, we're going to create an array here that goes from 0.01 to 0.2. If you use linspace with no further arguments, it creates 50 points uniformly distributed between the range you have here. If you want, you can add an argument here. For example, if we wanted 100 points, we could specify 100 points, but without more arguments, then it's just 50. And we're going to do the same thing we did before. We loop through all these values. We train the model. In this case, we're going to call the ridge regression. We're going to use this lambda value. In the arguments here, it's called alpha, but okay, we call it lambda because of the expression. This is just some additional arguments for the solver it's going to use. This is the tolerance for the convergence in the fitting for this model, but you can check the documentation and maybe leave the default if you want. In any case, the important part here is that we are changing the regularization term, looping through the values that we have here, and we're going to fit to the training data, predict in the validation data, and compute the mean quadratic error between the predictions and the target values for the validation set. And now we're going to do this to find the best value for the regularization term. So note that this is always the same model. It's a linear model using a polynomial expansion to degree 10. So basically, we are fitting polynomial curves of degree 10. And what we are changing is how much regularization we are putting in. So if we put too little regularization, we have a large validation error. If we put too much regularization, we start having a large validation error again. The curve is now becoming too stiff, but there is a sweet spot here where we find an optimum value for lambda. And if we use that value, then we can fit the data in this way. So this again is the training set in blue, validation set in green, and test set in red. Note that in this case, since this is done randomly, we got different distributions. But if you want to have a more consistent result, then you should do the split first and then try all the different models using the same split. If you do this over and over again, and you choose, for example, the one that gives you the best test error, then that will be cheating. You are biasing the estimates because you're doing repetitions until you get the result that you want. So don't do that for real applications. Be always careful of this detail that when you're choosing something, for example, here we are choosing lambda by looking at the validation error in order to minimize the validation error. This means that now the validation error is biased and we cannot use it as an unbiased estimate of the true error. So that's why we left the test set at the end to do these measurements. Okay, so to sum up, we have this problem that our model may be fitting too much to the training data and lose the ability to generalize outside the training data. And so we use these error measures, the training error, the validation error, and the test error, which are measured in different data sets. The training error is measured on the data we are using to adjust the parameters of the model. The validation error on the data we are using to choose either the best model or the best hyperparameter, for example, for regularization or something like that. All of these will be biased estimates because we are using them to choose the best results. And so we have this test set that we don't use for anything and we only use at the end to have an unbiased estimate of the true error. So remember, never use the test set to choose anything, even if it's just running your script several times until you get a low test set. If you do that, you're also cheating and getting a biased estimate of the true error. Remember that these estimates are stochastic, so we are not actually measuring the true error. We are taking a sample as an estimate for that error. And to minimize overfitting, we saw two different approaches here. One is to select the best model. So we are considering different hypothesis classes and see which one fits better with the amount of data that we want and the kind of problem that we have. and regularization, where we can, using the same model, the same hypothesis class, we just fine-tune the way we are training the model, the way we are choosing the best hypothesis, so that we can minimize overfitting. So I recommend that you take a look at these sections of Bishop's and Alpaiden's book, and also, if you want, look at the examples of the linear models on scikit-learn. So this will give you more information of practical nature of how to use these linear models in the scikit-learn library.